Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 5 of a unit work, power and energy. So let's begin with today's class. In today's class we are going to discuss about the potential energy. Now let's begin with the potential energy. Potential energy of a body is the energy possessed by a body by virtue of its position, or I should say by virtue of its configuration. Yes, it is the energy possessed by a body due to virtue of its position or its configuration. Let's take an example that you can see that this is a spring and certain weight has been attached with it at the lower and upper end aspects. So it is the case we can consider it's a case of the stretch or compressed spring. In this stretching or compressed spring having certain energy that we call as an elastic potential energy. This is what we call as an elastic potential energy, and water stored in an overhead tank, yes, even it is having an energy, and this energy we known as the gravitational potential energy. This is gravitational potential energy. So we have two different energies. One is the elastic potential energy, another is the gravitational potential energy. Yes, so these are the different forms of energy. So let's just find it out, the expression for the gravitational potential energy. Let's suppose assume that a body is there and the body is having a mass m. It has been kept over here, and with the help of certain force that has been brought from A to location B, which are at displacement of h. So we are lifting it vertically upward through a height h. So if I find out the work done by the external agency, that is by the external action, external force against the gravity or the force of gravity is, then I can have it's a work done is equals to F dot x, and the force here it's an mg. The displacement it is equals to h, and the work done could be given as mgh. Is it clear? Is it great? So this work done gets stored as potential energy of the body, and potential energy of the body can be said as the U is equals to mgh. One very important thing is potential energy can be positive or negative, because at a first thought we might consider that energy would be always positive. This is not the case. While we consider the kinetic energy, it is equals to half mv square, and this would be always positive. This is always positive, but potential energy can be positive or negative. How? Let's have a look. Let's suppose understood that this is my reference level. A certain object is placed over here, and it has been displaced from this position to this position, and this displacement is, let's say, h1. So in this situation potential energy would be equals to mg h1. This is the case when I have considered that upward direction should be considered as a positive. Now in the different case, let's suppose understood that this is the object and I need to displace it from this position to this position. If I need to displace it from this position to this 2, and this is an height h2, so in this case my potential energy should be minus of mgh2. Yes, because if this has been reference level and upward direction is considered as a positive, then downward direction must be considered as a negative. So if I have considered this as a negative, this would be the minus mgh2. So thus potential energy can be positive or negative, but when we say kinetic energy, it must be always positive. I hope this is clear. Is it clear? Yes? Great. Now, well, we need to switch for the elect for the elastic potential energy. But before we switch to the elastic potential energy, first we need to understand the spring force. And based on the spring force, we are going to have the elastic potential energy. So let's assume that this is the spring in its natural length. Yes, this is the natural length of the spring, L naught. Now what we are supposed to do is that we are going to stretch this spring by certain external force, something like this. It's an F external, and due to this F external, the spring has been displaced by this much distance. So this was L naught initially. Initially this was L naught, and now the length is L naught plus delta x. That means the displacement of the spring is of delta x. So according to the Hooke's law, it is F external is directly proportional. F external is directly proportional to the x. And if I remove this proportionality constant, I can write like this. It's an F external is equals to k multiplied by x. This k is called as the spring constant. It is a spring constant, which could be written as the ratio of the F external to the x. Its a unit, it's a Newton per meter. Its unit is Newton per meter. Yes, so this is spring constant. It is basically a spring dependent property. Different springs have different spring constant. Springs having the higher k, should I write this? It's a spring dependent property. Different springs may have different spring constant, and the springs which are having higher value of k are considered as stiffer springs. Yes, that means we require larger amount of force. We require a larger amount of force to compress or expand it. I hope this is clear. Yes, so this is all about k, that we know at this point of time that it is the constant, and that constant is known as the spring constant. Yes, higher the k, stiffer would be the spring. Lower the k, the spring would be the less stiffer. Yes, that means if k is less than, then we require a smaller amount of force to compress or expand it. I hope this is clear. Is it clear? Is it? Great. Now, when spring expands or compressed, it is having a restoring force which tries to regain the natural length of a spring. So when we are expanding the spring, or we are going to compressing the spring, it is always having one of the force, and that force we call as the restoring force. And that restoring force is such that let's have a look, that this is the rigid support, and this was the natural length L naught. When I say natural length, that means we have not compressed it, or we have not expanded. Yes, it is in the natural situation. That is why we call it as a natural length. Now, let's suppose we are applying a force, and that's why it has been expand something like this. This was the delta x. Yes. So when I am expanding this, a restoring force would be developed. Obvious, it wants that spring will regain its natural length, and to regain its natural length it need to compress it. So restoring force is always in the opposite direction of F external, but value wise it is same. It's a restoring force could be written as minus of k into x. Yes, again k is the spring constant. K is the spring constant, and x is the displacement, or for understanding purpose you need to understood this as a change in length of spring. I hope this is clear. Yes, so restoring force always acts opposite to the direction of external force. Is it clear? Now let's suppose take one more example, that this is one of the spring and this is its natural length L naught. Now if I'm supposed to compress it, and due to this compression the spring is become something like this. This is the case when I am going to compress this. It's an fx, and so this is the variation, and this is delta x. So restoring force would be applied in this direction. This is Fr. Yes, and this Fr could be written as minus of kx. This is F external. So F external and Fr would be same in value, but opposite in direction. Yes, restoring force always tries to so that your spring will be there in the natural length. I hope this is clear. Is it clear? Is it any issues? Anything? No? Great. Now one more thing. Note, for any spring, K into L remains constant, where K is the spring constant, and L is the natural length of a spring. If I plot this K versus L, this is K, this is L, then it should be something like this. Yes. Do you understand the meaning of this? That as L is increasing, K is decreasing. Even reverse is true. If L is decreasing, K must be increasing. So that if you understand this, let's assume that this is a spring and this is its natural length. This length is of, let's suppose, 10 centimeter. If this length is of L equals to 10 centimeter, and let's assume that its a spring constant is K. Now let us suppose I am dividing this into two segments of equal length. This would be of 5 centimeter, even this would be of 5 centimeter. So, and if I pick any one of the spring, this would be of, let's say, something like this. It's a 5 centimeter and its spring stiffness would be equals to K dash. So if I want to find out the K dash, let's have a look. It's a K dash by K. That should be is equals to K equals to 1 by L. Yes, because K into L is constant. That means K is equals to 1 by L. And when I write this, K is equals to 1 by L. This is equals to 5. This is equals to 10. So this is equals to 2. So that means K dash is equals to 2 into K. I hope this is clear. Is it clear? Is it clear? Any issues over here? No? Great. So please do remember this. For any springs, K into L is equals to constant. Let's work on this for one more question. Let's suppose a spring is there, and the spring has been divided into n number of segments. Now if we took any one of the segments, something like this, I need to find out the K dash. Originally this spring is having a spring constant of K. So the question is find out K dash. Yes, let's assume that this length is NL and this length is L. So as I have divided NL length spring in n segments, or n equal segments, I should say this. N equal segments. So K dash by K, that should be equals to L divided by NL. This has gone, and K dash should be written as N into K. I hope this is clear. Is it clear? Is it? Are you sure? So this K dash could be written as K dash is equals to N. K dash could be written as K dash is equals to N into K. Got it? Any doubts? Any issue over here? Anything? No? Great. Let's do this question. That a spring is there. This spring is having force constant of 1000 Newton per meter. If spring is being applied a force of F is equals to 4 into 10 to the power 4 Newton. Find out expansion of spring. You need to find out the expansion of the spring. So what can you do this? How should you? So we understand that F could be written as K into X. The given force is 4 into 10 to the power 4. Spring constant, it's a 10 to the power 3 multiplied by X. So this X could be written as 4 into 10 to the power 4 divide by 10 to the power 3, this has gone, and this is equals to 40 meter. Yes, because this force is very large. This force is very large. I hope this is clear. Is it clear? Is it any issues up till now? Everything is clear. Are you sure? Great. Let's connect the combinations of springs. When you are in the 10th class, you are having a combination of resistors. So in that situations, resistors were connected in series and parallel. Same thing is true for spring as well. Yes, so even springs can be connected in series combination as well as in parallel combination. Now the situation is, while springs are connected in series, force applied on all the springs, force applied on all the springs will be same, while in the case of the parallel combination of the springs, extension or compression, extension or compression of all the springs will be equal. I hope this is clear. So in the series combination, force applied on all the springs will be the same, while in the parallel combination of the spring, the extension or compression of the springs will be same. Now how will it work? Let's have a look. First, it's a series combination. Of spring. So let's have a look. Let's suppose this is first spring, this would be the another spring, and this is having a spring constant of K1, this is having a spring constant of K2, and these two springs have been extended by a force. It's an F external. So let's assume that this is x1, that means it has been expanded by x1, this would be expanded by extension, I'm talking about the extension, by x2. As they are in series, force on both the springs will be the same. So force on both the springs will be same. So I can have a total extension x total could be written as x1 plus x2. Yes, this is the extension of first spring and extension of second spring. So when I write the total extension, I can have our relation is that F is equals to K into X, and from this X could be equals to F divided by K. So this is F divided by K total, or we can rather say it's in K equivalent. It is F divided by K1 plus F divided by K2. This force can be cancelled out, and on a generalized term, I can have 1 by K equivalent should be equals to 1 by K1 plus 1 by K2 plus 1 by K3 and up to 1 by Kn. I hope this is clear. Is it clear? Yes, this is series combination of the spring. Now while I connect my springs in the parallel, so let's have a look that springs are connected in parallel. So when the springs are connected in parallel, situation would be something like this. Let's suppose this is first spring and this is another spring, and force has been applied over here. It's an F external. So in this case, in this case, extension or compression of both the springs will be equal. And when they are equal, when extensions or the compressions will be equal, let's assume that this is K1, this is K2, its extension would be X, its extension would be X. So definitely a force would be the different one. It's an F1, it's an F2. So F external could be written as F1 plus F2. Is it clear? Is it clear? This F external would be equals to F1 plus F2. Yes. Now when they are equal, F external is equals to F1 plus F2, I can have the relation, it's an K equivalent multiplied by X should be is equals to K1 into X plus K2 into X. Yes, this X could be gone, and the K equivalent could be written as K1 plus K2 plus K3 up to Kn. This is the K equivalent. This is the K equivalent. K1 plus K2 plus K3 up to Kn. Is it clear? So when they are connected in series, this is the K equivalent. It's a actually 1 by K equivalent is equals to 1 by K1 plus 1 by K2 up plus 1 by K3 up to 1 by Kn. And when they are connected in parallel, this is the K equivalent. I hope you have written this. One more thing you must be clear in your mind is that how should I understood that whether these are connected in series or these are connected in parallel. How could I come to know? Always you need to consider its properties. If extensions or compressions of the springs are equal, that means they are connected in parallel. If extensions or compression of both the springs are equal, then they are connected in parallel. But if they have been applied the same amount of force, they have been applied by the same amount of force, that means force acting on both the strings will be equal, then they are connected in series. Always remember this. Done? Let's have a look. Have your pen and paper with you guys. Do it fast and do it carefully. Let's suppose this is first spring, this is second spring, this is K, this is 3K. So they say find out K equivalent for given figures. So as I understood that these two are connected in series, and when they are connected in series, I could have it's a 1 by K equivalent is equals to 1 by K1 plus 1 by K2. This is 1 by K plus 1 by 3K. That should be is equals to, this is 3 by 3K plus 1 by 3K. It's a 4 by 3K, but this is 1 by K equivalent. So the K equivalent should be equals to 3K by 4. Is it clear? Got it? What was your answer? Is it same? Is it? Great. Now let's understood this. This is 3K and this is F external. This is K, let's say. So to find out the K equivalent, these two are connected in parallel. How could I come to know? Because their extension or compression would be the same. So their K equivalent could be written as, give me a moment. Their K equivalent could be given as, this is 3K plus K. That should be is equals to 4K. That's it. You did it. Great job. I hope this is clear. Let's have one more question in the same series, that you need to find out the K equivalent. Yes, let's say this is block M. This is of 4k. This is again of 4k. And you have been asked that find out k equivalent. So first thing, whether they are connected in series or they are connected in parallel, how should I come to know that is this two springs are connected in series or in parallel? How they have been connected? Yes, they have been connected in parallel. Why? Because if you if you move this block on this direction, then let's give them a name. It's a 1 and 2. That if you shift your block in the negative x direction, then the compression in first spring will equals to expansion in second spring. I hope this is clear. That whatever the compression is there, whatever is the compression in the first spring, that equals to the expansion in the second spring. So if I write it's an x1 compression, then this is x2 expansion, and this x1 must be is equals to x2. So when their compression and expansions are same, they are connected in parallel, and once they have been connected in parallel, I can have k equivalent, that should be is equals to k1 plus k2. This k1 it's a 4k, this k2 it's a 4k, and this will make it's an 8k. This is k equivalent. I hope this is clear. Is it clear? Is it any doubts? Any doubts in this? Anything? No? Great. Let's work for the next question. We are just doing this much, an ample amount of practice on the springs, because springs are going to be used at the various units and we are not going to cover it at every individual units. That's why we are covering all the concepts. That's why we are going to covering all the concepts of the springs at here only. Yes. Now let's suppose a spring is having length of 6L and spring constant K is divided into 3 segments having lengths of 1 is to 2 is to 3. So this are divided into 3 segments. These are divided into 3 segments having the lengths of the 1 is to 2 is to 3. So what do you need to do? Find out spring constant of each of the segment. So the situation is, this is a spring having length of 6L and it has been divided into 3 segments, 1 is to 2 is to 3. Yes, this total makes a 6. That means you can say that one of the segment would be of L, another segment would be of 2L, and one more segment would be of 3L length. So this would be the situation. Now one more thing that I understand is K into L is equals to always constant. Yes, K into L is equals to always constant. I hope this is clear. Is it clear? Is it? So once I know that K into L is equals to the constant, and the spring has been divided into three separate segments. I can have this kind of relations. It's an, let's say, K1 L1 is equals to K2 L2. So this is I'm going to use for the total. This is I'm going to use for the total, and this is I'm going to use for the first segment. Yes. So my relations would be modified as K total multiplied by L total should be equals to K1 L1. So K total is the K, L total is the 6L. K1 it is a, let's write it as a K1 multiplied by its length, it's an L. So this K1 should be equals to 6K. I hope this is clear. Is it clear? Is it? Same way, K total multiplied by L total should be is equals to K2 into L2. This K total is K, length total it's a 6L. This is K2 multiplied by L2, and the second length will be equals to 2L. So this is 2L 3s are. So this K2 should be equals to 3K. Is it clear? One more thing, K total multiplied by length total should be equals to K3 into L3. So now K total it's a K, length total it's a 6L, K3 multiplied by this length it would be a 3L. So this is 3L, 2s are 6L. So K3 should be equals to 2 into K. Done. So we have the relation, it's a 6K, 3K and 2K. As you understand, as soon as length is decreasing, its K is increasing, and if length is increasing, then the K is decreasing. That we have plotted at very beginning level. Yes, very good. Now in the previous question, if we connect those three segments in series and parallel, find out ratio of their equivalence. Find out ratios of their equivalence. So what I need to do is I have three springs, and one is the K1 equals to 6K, another K2 is equals to 3K, one more it's a K3 is equals to 2K. So when I connect this in series, it's a 1 by K equivalent is equals to 1 by 6K plus 1 by 3K plus 1 by 2K. This is equals to 1 by 6K plus 2 by 6K plus 3 2s are, yes, it's a 3 by 6K. This is 3 plus 2 5, 5 plus 1 6, it's a 6 by 6K, and that should be is equals to K equivalent should be is equals to should be is equals to 6K by 6, which should be a 6. This is the K equivalent of the series combination. Now when they are connected in parallel, their K equivalent should be equals to K1 plus K2 plus K3. So this is equals to 6K plus 3K plus 2K. This is 6 plus 3 9, 9 plus 2 11. This is 11K, and this is the K equivalent of parallel combination. So if I take a ratio of the series combination to the parallel combination, it's a K equivalent of series to the K equivalent of the parallel. For the series combination, it was, I made a mistake over, it's a 6K by 6, it's a K. So K equivalent of series it's an K equivalent of series, it's a K equivalent of parallel, it's a 11K, and this has been lost. This is 1 is to 11. I hope this is clear. Is it? So can you do this kind of questions that connect them to the series, connect them to the parallel, divided it, and all that kind of stuff? I hope this is clear. Is it clear? Great. So as we know and we understand the springs well, we understand the spring force and the restoring force of the spring well. Let's understood the potential energy stored in a spring. This is what we are talking about, the elastic potential energy. This is what we call as in the elastic potential energy of the spring. So let's have a look. It says that the figure shows one end of a massless spring attached to a rigid vertical support. We are talking about this end, and the other end to a block of mass m, which can move on a smooth horizontal surface. So let at x equals to 0 denote the position of the block when the spring is its natural length. This was the situation when we have considered that spring is in its natural situation, natural length. In an ideal spring, the spring force Fs is directly proportional to the x, where x is the displacement of the block from the equilibrium position. Yes, we were talking about this. It's an F directly proportional to the x. This force law for the spring is called as the Hooke's law, and it's mathematically represented as minus of kx, where k is the spring constant. We know all this stuff. It's SI unit, it's a Newton per meter, and it is the measure of stiffness of the spring. Why negative? Because negative sign indicates the direction of Fs is always opposite to the change in length. So now I need to calculate the work done. To calculate the work done on the block by the spring force, as the block by the spring force, look at this. Yes, by the spring force is if block moves from the x equals to 0 to the x equals to x naught. So let's have a value dw is equals to f dot dx. This f could be written as minus of kx dx, and if I integrate this, I am having work done is equals to minus of half into k into x naught square. I hope this is clear. Now work done, we need to understand that the work done by the spring force is always negative, because every time it is the case of theta is equals to 180 degree, and once the theta is of 180 degree, we understand that it is the case where work done would be negative. Now let's assume that and have a generalized term that if the block moves from x equals to x1 to x equals to x2, then the work done by the spring forces, that is work done to is equals to from x1 to x2, it's a minus of kx dx, minus 1 by 2k on this side, integration of x square, integration of x dx, it's an x square by 2, and let's put up the value. If we put up the value, it would be something like this. It's a minus of k integration of x square by 2 from x1 to the x2. So that should be is equals to minus of k into bracket 2 into x2 square minus of x1 square, or that could be written as, if I take it as a positive, k by 2 into k into x1 square minus x2 square. Even you can remember it such as this. It's a work done is equals to half into k multiplied by x initial square minus x final square. Yes, so here no need to write it down that x1 is initial or x2 is initial and all that kind of stuff has been removed. So you need to remember this, that work done is equals to half into k multiplied by x of initial square minus x of final square. If you remember this, all tasks will be done. So one more thing, and very interesting, that the work done by the spring force depends on the initial and final positions of the spring only. Look at this, it depends on this two only. It does not depend on the path taken. It does not depend on the path taken by the initial and the final position, or to reach final position from initial position. That's why spring force is considered as a conservative force. Do remember this at this point of time. We are coming back to this point about the conservative forces and non-conservative forces, but at this situation you are just going to remember this. I hope this is clear. Is it clear? Is it? So are you ready for certain questions? Let's have a look. It says a body at rest. A body at rest can have, does it have kinetic energy? Does it have? Let's check. It's a kinetic energy is equals to half into m into v square. If v is 0, definitely kinetic energy would be a 0, so this could not have. What is momentum? Momentum is equals to m into v. As v is 0, momentum could not be there. Both momentum and kinetic energy, no. Yes, it's a potential energy. What is potential energy? What was its definition? This is required every time. You must remember this. It is energy possessed by a body. It is the energy possessed by a body due to its position or configuration. It is the energy possessed by a body due to its position or configuration. This is what we call as the potential energy. Yes, so a body at rest can have a potential energy due to its position or due to its configuration. Now, let's work for this. It says that two springs, A and B, these two are identical, but B is stiffer than A. That means they want to say it's a spring constant of B is greater than spring constant of A. Now this says that when the both are stretched by the same force, that means FB, that is the force applied, on the spring B is equals to force applied on the spring A. When both are them stretched by the same force, then more work is done in the case of. Great. Now let's have understood that they have mentioned that FB and FA, these two are the equal. Now FB, it's FB that could be written as KB into XB should be is equals to KA into XA. So KB to the KA should be equals to KB to the KA should be written as XA to the XB. I hope this is clear. Is it clear up till now? Up till now, is it clear? Any doubts? Any doubts in this? Anything? No. Now, what I want that more work is done in the case of. So, let's just find it out. The work done. So, work done in the case of A divide by work done in the case B. It's a half into KA into XA square divide by half into KB into XB square. So if I understood the situation well, then this half and this half would be the gone. So I have been left with the KA by KB multiplied by XA by XB whole square, and I am having this, it's a KB by KA should be is equals to XA by XB. So let's just replace XA by XB by the KB and KA. So this is equals to Ka by Kb multiplied by it's Kb by Ka whole square. As this is power 1, this is power 2, so 1 power would be gone, so I should write it over here. Yes, so it's a 1 power would be gone, sorry, 1 power would be gone, and the remaining would be this stuff. It's Kb is to Ka. This is of work done A is to work done B. Now, according to the data, they have given that Kb is greater than Ka. So when they say it Kb is greater than Ka, when they say it Kb is greater than Ka, I can write like this. It's work done A to the work done B is equals to Kb is to Ka, which should be greater than 1. So work done on A should be greater than the work done on the B. I hope this is clear. So work done would be higher in the case of the A. Is it clear? Is it clear? Done? Great. Let's look at the next question. It says that two springs A and B, and even the relations are given, Ka is equals to 2Kb, are stretched by applying forces of equal magnitudes at their ends. If the energy stored in A is the E, then that is in the B. Okay, so they have been applied by the equal forces. So what I can have, it's an Fa is equals to Fb. Ka(xa) should be equals to Kb(xb). Yes, so it's an Ka is to Kb should be is equals to Xb is to Xa. Yes, now what I need to find out, their energies. If the energy stored in A is E, then the energy stored in B. So work done on B divided by work done of A, that should be is equals to half. It's an Kb xb square divided by half into Ka into Xa square. This half has gone, and I can replace the xb and Xa. It's a Kb by Ka multiplied by xb by Xa whole square. So this is equals to Ka square divided by Kb square. So the power can be cancelled. It's a Kb to the power 1. This has cancelled. It's a Ka to the power 1. It's a cancel. So that should be is equals to Ka is to Kb. And this is equals to work done on the B divided by work done on the A, which is equals to A. Now Ka, that should be a 2 Kb. This is equals to Kb. So this 2 has gone, and work done on the B, that should be is equals to twice of the E. This is work done. I hope this is clear. Is it clear? Is it any doubts, any issue over this? Anything? Let's look at this question. That suppose we have been provided two springs. This is one, and this is second. This is the Ka, this is the Kb, and they have mentioned that Ka is equals to 2 Kb. Now the data says that if both the springs are stretched by same amount, if both the springs are stretched by same amount, then find out ratios of their force applied and energy stored. So go through data once and let me know how should I do this. They have given the two springs. They have given even the relations between the spring constant of these two springs, and they say that both the springs have been stretched by same amount. That means their extensions are equal. It's an x1 equals to x2. This is what they have given. Now what I want to find out, I want to find out the ratios of their force applied. That means F1 is to F2. This is required. And one more thing, their energy stored. That means work done 1 is to work done 2. This is required. So let's begin then. What I understand and what is given. Based on that I can have F1 divided by F2. That would be equals to K1 x1 divided by K2 x2. Yes, they have given it's a Ka multiplied by x1 divided by Ka multiplied by x2, and this is according to the data x1 and x2 are equal, so this could be cancelled out. This is Kb, this is Ka is to Kb, so Ka is to Kb is only left with, and they have given that Ka is equals to 2 Kb, so this is equals to 2 Kb divided by Kb, and that should be equals to 2 is to 1. This is Fa is to Fb. This is the first task I need to do. Now Fa is to Fb is over. Now work for the work done. Yes, so let's begin then. Work done on A to the work done on B. That should be is equals to half Ka x1 square divided by half into Kb into x2 square. According to the data x1 and x2, these two are equal. Yes, they have been extended by same amount. Yes, so this 2 has cancelled, this 2 would gone, only the term that I left with, it's a Ka is to Kb, and as I understand that Ka is equals to 2 Kb, that is given, so this is again 2 is to 1. I hope this is clear. Is it clear? Is it? What was your answer? Was it same? Was it? Great. Let's work for the next question. Do it quickly. You are doing pretty good. Well done. Keep it fast. That if energy stored in spring from its natural length by amount x is E joule. If energy stored in spring from its natural length by amount x is E joule, find out further energy stored in spring if it has been expanded by more to x distance. Go through the data once and let me know how should I do this. What does it say? It says that energy stored in the spring from its natural length by an amount x is the E joule. That means initially it was at 0, and then finally it is at x. Now find out the further energy stored in the spring if it has been expanded by more at 2x distance. So it is something like this, that initially it has been displaced by x amount and the energy stored is E. Now it is going to expanded it by 2x amount more, and you required energy E dash over here. So what I understand is that if I go with this, that initially this is the reference level, that means this is x equals to 0. So work done 1 is equals to half into K multiplied by x1 square this energy stored, it's a E. That should be is equals to half into K into X square. This is the energy E. I hope this is clear. Now, if I understood E dash, that if I take a reference as in 0 and if I assume it at the initial stage that this is the 3x displacement, find out their work done. So the work done 2, it's a half into K multiplied by x dash square, and that should be is equals to 1 by 2 multiplied by K, x plus 2x, it's a 3x whole square. So that should be is equals to half into K multiplied by 9x square. This is work done 2. I hope this is clear. Now just take the ratio of work done 2 is to work done 1. It's a work done 2, it's a work done 1. This is equals to half into K into 9x square divided by half into K into x square. So this and x square has gone, and from this work done 2, it's so work done 1. This is equals to 9, while work done 1 is given as 9, so work done 2, it's equals to 9 times of E joule. This is the energy stored, but you need to understood these, that we have taken this situation. This was x, this was E, this was 2x, and this was E dash. I required only this part. That means when it has been stretched by x to 2x, I need to do this. So required energy stored is 9E minus of E, and that should be equals to 8 of E. I hope this is clear. Is it clear? Because I want only this. I am interested in this only. I hope this is clear. Is it clear? So will you be able to solve this kind of questions? Are you sure? Are you sure? So can it be done? Can it be done by you guys? Great. So let's just wind it up this session over here. Yes, this was all about the potential energy stored in the body. Yes, please refer this very carefully. Do as many questions as possible. So up till now we have discussed in the energy sections, we have discussed the kinetic energy, we have discussed the potential energy. Now onwards we are going to have a conservation of total energy. That means I'm going to use the concepts of the potential energy and concepts of the kinetic energy. So before you tune in to the next session, please revise this, both the lectures of the energy. This will help us to get the numericals solved. I hope this is clear. Thank you. Have a good day. Take care. Bye.